This is the first video for Unit 3, Reactions in Stoichiometry. This module will focus on chemical reactions and equations. The learning objectives for this module include interconverting names and chemical formulas for simple organic molecules, learning how to represent chemical reactions using chemical equations, describing precipitation reactions, acid-base reactions, oxidation reduction reactions, and learning how to balance oxidation reduction reactions in acidic and basic conditions using the half reaction method. Our first video will focus on organic chemistry nomenclature, where we will learn how to interconvert the name and chemical formula for simple organic molecules. The way we use organic in chemistry is different than how the word organic is used for food marketing purposes. In chemistry, the word organic means any compound where carbon is bonded to hydrogen. Organic molecules can also include oxygen, nitrogen, phosphorus, or sulfur, or any of the halogens. Under this definition, water is inorganic, meaning not organic. And that's because there's no carbon. So water is not organic, water is inorganic. When organic compounds contain only carbon and hydrogen, then it's called a hydrocarbon, and that stands for hydrogen and carbon. Carbon will always bond to enough hydrogens so that it has 4 bonds total. And so bonds are represented by these lines here. And you can see that carbon has 1, 2, 3, 4 bonds. And so it has 4 single bonds to hydrogen. In this molecule, there's 1, 2, 3, 4 bonds around this carbon, but one of those bonds is to a second carbon. And so each carbon here still has 4 lines coming out of it. But now each carbon's only bonded to 3 hydrogens. In this molecule, there's even more carbons bonded together, but this carbon here is bonded to 1, 2, 3, 4 things, 3 of which are hydrogen, and there's 1 carbon. This carbon is bonded to 2 other carbons, and so it only needed 2 bonds to hydrogens. Hydrogens are like filler atoms. They will fill in wherever necessary to give carbon 4 bonds total. Carbon can triple bond to itself or double bond to itself. And so these are examples of how carbon still has 1, 2, 3, 4 bonds. And so then it would just need 2 hydrogens since 2 of those bonds are to another carbon. But the goal is that carbon always has 4 bonds total. It takes a really long time to continuously draw out molecules in organic chemistry because you have to draw all these different lines and all these different hydrogens. And so it's extremely time consuming to do this over and over again. And so chemists developed a shorthand called line drawings. That way they wouldn't have to keep drawing all of these carbons and hydrogens over and over and over again. This is a very time-saving method, and it's based on the structure of the molecule in 3 dimensions. Due to the bond angles between these carbons, it naturally forms a zigzaggy shape. And so we can shortcut drawing this molecule by only drawing the bonds between the carbon atoms. And so really this line structure here, there's a carbon at each intersection. Each time the line changes direction, there's a carbon. And at the ends, there's also a carbon. And then we know that carbon has 4 bonds total. Since this carbon already has 1 line coming off of it, it must have 3 hydrogens. Since this carbon has 2 lines coming out of it, it must have 2 hydrogens. That way it has 4 total. And so you can see that this drawing can be expanded to show all of the bonds, but really you only need to draw the squiggly line structure. And so it's much easier to just draw 1, 2, 3, 4, 5 to represent the 5 carbons in the chain. So line drawings are awesome because they are super fast to draw. For our hydrocarbons, there's a naming scheme that helps represent how many carbons are in the chain and the bonding arrangement in there. And so for alkanes, then alkane, this ane suffix here means it's all single bonded, and then alk is like saying carbon something. So the prefixes for how many carbon atoms are shown in this table here. After 4, then the prefixes become more normal. Pent, you might be familiar with pentagon. Pent means 5. Hex, like hexagon, that means 6. And so these prefixes after 4 are probably familiar. Everyone always forgets 7, but 7 is hep, and then 9 would be non. But these first 4 are, you just have to kind of say them over and over again until you remember the order. Meth Eth Prop But, Meth Eth Prop But. And so then you can learn how to count to 4 for your carbons. And so if you pair these with the names, you can actually get some pretty familiar sounding names, like methane, ethane, propane. So these are very well-known compounds. And so you might have heard of methane in terms of natural gas or a greenhouse gas. This is methane because it contains 1 carbon. This contains 3 carbons, and so that's 1 meth eth prop, so that's propane, all single bonded. And so propane's used for barbecues. This is 1, 2, 3, 4, meth eth prop but. This is butane, found in lighters. And this has 1, 2, 3, 4, 5, 6, 7, 8 carbons. And so that is oct, all single bonded, and so that's octane. And that's found in gasoline. It even has octane rating right on the gas meter. So how many hydrogens are there? If you saw a name like octane, you will be able to calculate how many hydrogens are in that molecule just by knowing that it's oct in front. Because all of these simple alkanes follow this 2n plus 2 rule. That means that whatever the suffix is for, the subscript is for your carbon, you just have to double it and then add 2. 8 times 2 is 16, plus 2 would be 18. So octane would have the chemical formula C8H18. This is because all of the carbons have 2 hydrogens bonded to them, except for the ones on the end, which have an extra. And so each of these carbons gives a +1, making it +2 in the end. All of our organic molecules can also have functional groups. Functional groups are clusters of atoms that are responsible for the characteristic reactions and properties of the molecule. And so it's these areas of the molecule that help dictate what chemical reactions happen, as well as what physical properties it has, such as its melting point, boiling point, and it will even contribute to the density of the molecule, of the substance. And so the functional groups that you're expected to recognize are alcohol groups, carboxylic acid groups, and amines. which are based on ammonia. And so carboxylic acids could also be drawn out so that they look like this. And so earlier I circled this feature of a molecule, and so this is a carboxylic acid. We know it's a carboxylic acid, not an alcohol, because this OH and this double bond O are bonded to the same carbon. In contrast, this OH group is bonded to a carbon, but this double bonded O is on a different carbon. And so this is an alcohol because there's no double bonded O attached to that same carbon. This is a carboxylic acid. This is citric acid. Citric acid is found in citrus fruit. Amino acids contain both a carboxylic acid and an amine. The amine group is on this side. Amines can have either 2 hydrogens, or they could have carbons attached to them. So this is also an amine. It's really just nitrogen either bonded to carbon or hydrogen. So I put NH2 or C's instead of H's. So that's known as an amine also. This is, if we fill in the carbons that are not drawn in that line structure, this has 2 carbons and an OH, so that's an alcohol. And so the proper chemical name for this molecule is ethanol. Ethanol contains 2 carbons, single bonded, and it's an alcohol. Ethanol is the alcohol that's found in alcoholic beverages. So take a moment and try to figure out what functional groups are on these molecules. Specifically, I want you to figure out which of these molecules contains a carboxylic acid group. Go ahead and pause the video and try to find the carboxylic acid functional group. Unpause the video when you think you found it. Okay, so our carboxylic acid is right here on aspirin. The C right here is double bonded to an O, and it's single bonded to an OH group. This is not a carboxylic acid because it doesn't have an OH. It has an O bonded to this carbon ring structure. So this is actually known as an ester, and we didn't introduce esters on the previous slide. So this is not a carboxylic acid. Similarly, in this banana structure, this is an ester. And this does have a double bonded to an O, but there's no OH. This is what's known as a ketone. And so the esters and ketones are not going to be on the functional groups that you're expected to recognize. You're only really going to be held accountable for recognizing carboxylic acids, amines, and alcohols. Here's another practice problem for you. Go ahead and pause the video and try to come up with the names for these organic molecules. Unpause the video when you are ready to check your answer. Okay, so the first thing we have to do is count the carbons in this line structure. That way we know how many carbons there are to name it. This has 1, 2, 3, 4 carbons. If I count in organic nomenclature, that means Meth Eth Prop But. And so this is bute. They're all single bonded, and so that's butane. This has 1, 2, 3, 4, 5, 6, 7 carbons. And so 7 carbons would be hept. They're all single bonded, and so that's heptane. This wasn't part of the problem, but we can also figure out the chemical formulas using our 2n plus 2 rule. So that means C4, 4 times 2 is 8, plus 2 more is 10. This is 7, and so 7 times 2 is 14, plus 2 more would be 16. And so if we count up all the hydrogens here, there are 16 hydrogens. That concludes our video on organic chemistry nomenclature.